Hello students. So today we are going to do types of functions. Okay. So what is a function? Function we have seen in class 11. Okay. Function is when you have, suppose these are two sets A and B. Okay. There is a relation from A to B, and function is when have image of one element in A is unique. Okay, and this should not happen. That is, there are no two images of single element in A. Okay, so if your relation is like this, that is, single element is mapped to two images. Okay, then this is not a function. Okay, you can have like this. This is possible. Okay, this is a function. So this is not a function. So we should know that what is a function. Now we will see types of functions. Okay. Types of functions. First function is our 1-1 function. 1-1, or it is called injective. Okay. That is, if the images of distinct elements of x under f are distinct. That is, if a function is from some set x to x, okay, then the images are distinct of the elements in this set. Okay, then we say it is 1-1. Okay, that is, for every x1, x2 belonging to x, we have f of x1 equal to f of x2, which implies x1 is equal to x2. Okay, so if you get two functions equal, okay, and it is given to be 1-1, then these elements are also equal. 1-1 looks like this. This element is going to this. Okay. Then if it is not 1-1, then we write it as many 1. Many 1. That is, many are going to the single element like this. Okay, this is many 1. Next function is our onto function. Okay. It is also called surjective. So if every element of y is the image of some element of x under f, that is, for every y belonging to y, for every y belonging to y, if the function is defined from x to y, okay, y, there exists x belonging to x such that f of x is equal to y. Okay, this is the condition for onto function. That is, in terms of diagram, we have every element in y have a pre-image in x. Okay, then we say that it is a onto function. Okay, and in this we get range of f is equal to y. Since all the elements are mapped, okay, so all the elements are covered, so range we know the set of all mapped elements in y set, right? So range becomes equal to the whole set. Okay, this is your domain, the set of all mapped elements, all are mapped. Okay, so this is your domain, this is codomain. Codomain means it is the set of all y, okay, and range is set of all mapped elements. Next is a function f from x to y is 1 1 1 1 and onto, that is both injective and surjective, then we call that function as bijective. Okay, so whenever you have to prove any function to be bijective, it has to be 1 1 and onto. Okay, so let's take some example. So there is an example in the book. It says, let A be the set of all 50 students of class 10th in a school. Let f from A to set of natural numbers be a function defined as f of x equal to roll number of every student in this class A. Now we know that every student will have, now this is your till 50 they are saying, right? So this A set has 50 elements and the Y set is our number of, this is natural number, set of natural number. So we know that this is infinite set, right? So roll number 1 is assigned to one number, 2 is 2 till 50. So this is 1 1, right? Because no two students will have the same roll number. Okay, this is 1 1, this is proved. Okay, now to prove that it is onto, we have to look at the elements of this set, that is Y set. This is a set of natural numbers. And we know that this is my codomain. Codomain is set of natural numbers. What about the range? Range is set of all mapped elements till 50. It is till 50 only. These elements are left out. Okay, so we don't get range to be equal to the whole set Y. This is not possible. So we can say that it is not onto. Okay, I hope you understood the um, theory behind it. Okay, next question. Show that the function f from set of natural numbers to natural numbers defined as f of x is equal to 2x. Okay, is 1 1 but not onto. Now to prove it to be 1 1, you can take some say let f of x1 is equal to f of x2. Okay, two elements in the set y are equal. This implies that 2x1 is equal to 2x2. Okay, now this 2 gets cancelled and you will get x1 equal to x2. So this implies that it is 1 1. Okay, this you can show in general also, that is by taking one elements. So if you take suppose 1, f of 1 is your 2, right? F of 2 is 4, like this. Now we'll prove it is not onto. F of x is equal to 2x. Now if I draw the diagram, okay, this is a set of natural number, this is a set of natural numbers. So 1, 2, 3, dot, 2, 3, dot, dot, dot. Okay, so 1, if you put here 1, you will get 2 as the answer. Okay, 1 is going to 2, 2 is going to 4. Okay, 2 is going to 4. So when you look at these elements, you'll find that this 1 is left out, 3 is left out. So we know that range set is not equal to the whole of n. Okay, so it is not onto. So you can write in general, that is, as for 1 belonging to n, that is in the set X, okay, one there does not exist any element, okay, in this set, that is Y set, such that f of x is equal to 2x. Okay, next is prove that the function f, now they have given set of real numbers, okay, given by f of x is equal to 2x, is 1 1 and onto, both we have to prove. Okay, 1 1 we have to prove the same way as we have taken for the natural numbers. Okay, so I'll not write it again, we'll go for onto. Okay, now onto is possible because here the set of real numbers is taken. Okay, whenever it is set of natural numbers, you have to check whether all elements are mapped or not. Okay, for real numbers we can write it as suppose for any y belonging to R, there exists, we can take f of x is equal to y. Okay, what is our f of x? 2x is equal to y. So x is y by 2. Okay, now this element is there in R. Is it possible? Yes, it is there. All the rational numbers, integers, all are there in R. So this belongs to R. Okay, so we can write that for a given number y belonging to R, there exists y by 2 in R such that f of y by 2 is 2. That is, in place of x, you have to write y by 2. Okay, so this is into y by 2, right? So we will get y. So f is onto. So the way to prove it is you have to take some element, okay, in the other set, okay, such that f of x is equal to 2x, the given function you have to write. Then you have to solve for x element and then you have to check whether this element belongs to your domain set or not. Okay, if it is there, then you can say that it is on. Okay. Next we have example 10, in that it is given, show that function from a set of natural numbers given by f of 1 is equal to f of 2 is equal to 1 and f of x equal to x minus 1 for every x greater than 2 is onto but not 1 1. Okay, so it is onto but not 1 1. Not 1 1 we can see from this condition, that is, it is given that f of 1 is equal to f of 2, but 1 is not equal to 2. This shows that it is not 1 1. Okay, then for onto you can take for any y belonging to set of natural numbers, f of x is equal to y. Okay, f of x is what? X minus 1. So x is your y plus 1. Okay, and they have given that x is greater than 2. Okay, if you take y, yeah, x is greater than 2. So if you take in general, suppose 2 starting from 3 3, 4, 5 and so on. So x minus 1 means here it is 2, 3, 4, 5, 6 and so on. Okay. F of 1 and f of 2 are both 1. So 1 and 2 both are 1 going to same element, and 3 goes to 2, 4 goes to 3, 5 goes to 4. So this is onto. Okay, this is onto. So y plus 1, this belongs to your set of natural numbers. So you can write that f of y plus 1 is, you have to put it in your function, y plus 1 minus 1. So this is y, and so for this belongs to set of natural numbers. Okay, or you can show the diagram and say that it is onto. Okay. Next is example 11. Show that the function f from R to R set of real numbers. F of x equal to x square is neither 1 1 nor onto. Okay. Now first case is we have to prove it is not 1 1. So if I take 1 x to be 1, okay, f of 1 we are getting 1. Okay. What is f of minus 1? Same thing. So 1 and minus 1 are going to the same element. Okay. So this says that it is not 1 1. Not 1 1. Okay. Next is we have to prove it is not onto. Okay. So if I take, say, we can prove this by using like this also. F of x1 is equal to f of x2. Say let. Okay. So this will be x1 square equal to x2 square. Okay. So x1 you can take root of x2 square. So this is plus or minus x2. That is x1 is either equal to plus x2 or it is x1 is equal to minus x2. The same as this. Okay, not all 1 1. For onto, let's say for y belonging to R, f of x is equal to y. So x square is equal to y. So x is equal to root of y. Okay. Now this is under root. So if I take a negative number, say minus 1. So root of minus 1, this doesn't come under set of real numbers. Okay. So you can write that if I have a element, say, uh, okay, negative elements are not there, that you can say. Okay, if we take in general, okay, so this is R, set of R. So 1, 2, 3, minus 1, 2, 3 and so on. Many are there. Okay, 1 square is 1, minus 1 square is also 1. Then 2, 3, 4, 2 square. These elements are left out. 2, 3, then negative numbers are left out. So many elements are there for which we don't have a pre-image. Okay. So we can write that for 2 belonging to n, there does not exist x belonging to RR, such that f of x is equal to x square. Okay, next. Suppose f of x1 is equal to, okay, you have to show that f of n from n to n, x plus 1, x minus 1, if x is odd and if x is even. Okay. Now to prove it is 1 1, first thing let f of x1 is equal to f of x2. So this is x1 plus 1, x2 plus 1. So x1 is equal to x2. Okay. If we take, suppose, this is possible only if both x1 and x2 odd. Okay. Same way for even, x1 plus 1 is equal to x minus. This is for even. Okay. Now if I take, suppose, f of x1 is equal to f of x2, where x1 is odd and x2 is even. Okay. Then I'll have to write x1 plus 1, x2 minus 1. Okay. So this is x1 minus x2 is equal to minus 2, or x2 minus x1 is equal to plus 2. Okay. So this is x1 is odd and x2 is even. So if I take x2 even, say 4, and x1 odd number, say take 1, so you'll get 3, right? You'll not get 2. This is not possible. If you take, say, 2 minus 1, you'll get 1. You'll get a odd number, okay, not a even number. So this is not possible. So whatever we proved first, that is, if both x1 and x2 are odd, then this is 1 1, and both x1 and x2 are even, then it is 1 1. Okay. Now we'll go for on to so if I take x plus 1, x is odd, so starting from 1, 1 plus 1 will get 2, then 3 plus 1 will get 4. So all are going to even numbers. Odd numbers are going to even numbers. Okay. Then if I take even numbers, 2 minus 1 1, 4 minus 1 3. So all even numbers are going to, this is 3, no? 3 going to 4. So all even numbers are going to odd numbers. So all numbers are getting covered. Okay. So odd numbers are going to even numbers and even numbers are going to odd numbers. So all the numbers in the set n, that is set of natural numbers, is covered. Okay. So this is onto. Okay. Next is show that an onto function f from 1 to 3 to 1 to 3 is always 1 1. Set 1 to 3 to 1 to 3. Okay, it is always 1 1. So they have taken here contradiction method. Okay, they have taken that suppose this is not 1 1. Okay, so if they have 1 and 2 have the same image, say 1, okay, then 3 is there. This is your domain, this is your codomain. So 3 can be mapped to either 2 or can be mapped to 3. Okay, suppose it is mapped to 2, then this element remains. Okay, so this implies that if this remains, then this codomain, that is, yeah, codomain is not equal to the range set. Okay, and this function is already given to be onto, and this contradicts with the statement that it is onto. Okay, so this is not possible, so we can say that it is 1 1. Okay, next question. Show that a 1 1 function f from 1 to 3 to 1 to 3 must be onto. Now they have given it to be a 1 1 function. 1 1. Okay, 1 1 means 1 is going to 1, 2 is going to 2, 3 is going to 3. Okay, so here there is no possible way to show that it is not onto. It has to be onto because all the elements are mapped. Okay, so this is on. Okay.